Today we'll be talking about the properties of normal distribution and applications of normal distribution. Here I have the notes and we will walk right through them. A continuous random variable is normally distributed if its relative frequency histogram has the shape of a normal curve. So here is your normal distribution curve, rough sketch. Your mean is in the middle. That's Greek letter mu, represents the population mean. And then Greek letter sigma, that's lowercase sigma, represents the population standard deviation. So you have your mean in the middle. When you add a standard deviation to the mean, it gives you an inflection point that's on the right of it. When you subtract a standard deviation from the mean, that gives you an inflection point on the left of it. Inflection points are just points on the graph where the curvature changes. So in other words, it goes from concave up to concave down or vice versa. So then here we have 7 points. The first point, it is symmetric about the mean. The mean is in the middle and it reflects whatever goes on the right goes on the left as well. It has a single peak and highest point at the mean. Your mean, mode, and median are all equal. It has inflection points. I already mentioned that it has inflection points when you add a standard deviation and subtract standard deviation from the mean. The total area under the curve. Total area under the curve is equal to 1. And remember, the mean is in the middle and it reflects about the mean. So that means 0.5 of your data or 0.5 of your distribution will be to the right of the mean. 0.5 of the distribution will be to the left of the mean. Number 6, as x increases, or in other words, as you go to the right, the graph is going to approach the horizontal line, or in other words, approach 0, but never touches. And the same thing happens to the left. So that's why when I drew this rough sketch, there was a little opening here. Your graph will continue to make its way towards the horizontal line, but never touch. Point 7, the empirical rule holds true. Approximately 68% of your data will be within one standard deviation of your mean. So here you see my rough sketch here. Went a little too far on this left side with my drawing. But within one standard deviation of your mean will be 68% of your data. Within 2 standard deviations of your mean would be 95% of your data. And within 3 standard deviations of your mean, it would be 99.7% of your data. And notice you have 0.15 on the ends, which will give you 0.3, that will give you 100%. So that's your empirical rule. Standardizing a normal random variable. Suppose that the random variable x is normally distributed with mean mu and standard deviation sigma. Then the random variable is going to be equal to what we call our z-score. Z is equal to x minus mu over sigma, or in other words, your the data value in question, minus your mean over the standard deviation. We're always going to round our z-scores to 2 decimals. All right. So we're also going to have a z-score chart, and I did a little rough sketch right here, in which it will start from at negative 3.4 on the left side, left column, go all the way to positive 3.4, and then on top, it will be 0.00, which will represent your hundredths place, and go all the way to 0.09. So if I have 1.23, the way I would go to read it, I would look at the 1.2. That would be what's on the left column, 1.2. And then my hundredths place, which is 3, will be on the top row. And then I see where they meet, and that would be 0.8907. That's how we read the chart. So this 1.23 as a z-score is going to represent a data value. We'll see how we convert them in a second. And then the z-score chart that I'm referring to has this diagram in the top left corner. That means everything that it gives, or every value that it gives what's to the left of or what's less than. So when I go to the z-score chart and I find my z-score chart value to be 0.8907, if I convert it to a percentage, that means 89.07% of the data will be to the left or less than that data value in question. And remember, everything under the curve is equal to 1. So if I want to know what's to the right of or what's greater than, I will subtract it from 1. So subtract 0.8907 from 1, that's 0.1093. So that means 10.93% of the data will be greater than the data value. So once again, this 1.23 as a z-score represents the data value, and we will be able to answer questions according to the chart value that we get by using the z-score. Here's just an example of the first half of that z-score chart, negative 3.4, auto to my 10th place of 0.0. On top, here are my hundredths place. Here's the positive side, going from 0 to 3.4, the positive values. Once again, my hundredths place, still here. And remember, we had 1.23, so here goes 1.2. And if I go to 03.8907. So that's how we will read that. So let's look at an example. A pediatrician obtains the heights of her 3-year-old female patients. The heights are approximately normally distributed with mean 38.72 inches and standard deviation of 3.17 inches. Determine the proportion of 3-year-old female patients that had a height less than 35 inches. So we're talking about less than in this case. So they give us the mean, they give us the standard deviation. Our data value in question is 35. We want to know the percentage of female patients that would be less than 35. So that's the X value. So put it in the z-score formula, 35 minus 38.72 over 3.17, that'll be negative 1.17. So now we go to the chart. We look at negative 1.1 on the left column, go to 0.07 on the top row. So the chart will always give, the chart that we are using will always give less than. Remember, that's what we're looking for. So when you go to the chart, you should get 0.1210. So that's going to be our answer. So if I were to put that in sentence form, the proportion of the pediatricians, 3-year-old females who are less than 35 inches tall is 0.1210, or in other words, 12%, 12.1%. All right, let's look at another one. Using the same mean and standard deviation in your setup problem. Determine the proportion of 3-year-old female patients that have a height greater than 42 inches. So before we were looking at less than 35, now we're looking at greater than 42. Mean and standard deviation are the same. Plug in the 42 and we get 1.03. Now when we go to the chart, we still read the chart the same. We look for 1.0 on the left column, 0.03 on the top row. Now the chart always gives less than, but we want greater than. So what we're going to do is subtract the chart value that we get from 1. Remember, everything under the curve is equal to 1. So if I know what's to the left of it, subtract that from 1 to figure out what's to the right, or in other words, greater than. So the chart value given to us by 1.03 is 0.8485. Subtract that 0.8485 from 1, and I get 0.1515, and that's my answer. So the proportion of pediatricians, 3-year-old females who are greater than 42 inches tall would be 0.1515. One more example. Determine the proportion of 3-year-old female patients that have a height between 35 and 40 inches. So this time we're talking about between. So we have two different data values that we're doing our comparison to. So we found a z-score for each one of those individually. The first one gives us negative 1.17. The next one, 0.40. So we go to the chart for both of them. So now the chart always gives less than. So if I look at the z-score, the first z-score, I'm looking at this type of shading. Looking at the second z-score, it's still to the left end, but it's just greater. So now if I want to know what's in between these two, I can subtract this one from the Z1 data value from the Z2 data value, and that will give me what's in between them. So whenever I want to find what's between, I will subtract the chart values from each other. Do not subtract the z-scores. We're not subtracting the z-scores from one. We're not subtracting the z-scores from each other. We are doing this from the chart values. So before, when we're looking at greater than, we subtract the chart value from one. Here, when we're looking at between, we're subtracting the two chart values from each other. So the first chart value is 0.1210. The second chart value is 0.6554. So we do 0.6554 minus 0.1210, and that gives us 0.5344 as our proportion. So in sentence form, the proportion of pediatricians, 3-year-old females who are between 35 and 40 inches is 0.5344. Okay, so just to sum it up, we have three scenarios. We have less than, greater than, in between. Less than, you'll just use the chart value. Greater than, you'll subtract the chart value from one. And then between, you subtract both of the chart values that you get. And then keywords that will let us know that we will be doing or using less than relationship versus greater than relationship. You know, if you're dealing with temperature, you're looking at colder or hotter, height, shorter or taller, below, above, left of, right of, longer, shorter, anything of that nature. If you're talking about less than or to the left of, you will be using the chart value. Talking about greater than or to the right of, you will be using the chart value and subtracting that from one. So let me know if you have any questions.